Hiya folks. In this video, I'm going to step away from Spring AI specifically and talk about a couple of options that you can specify when you're creating your prompts, whether you're using Spring AI, LangChain, Llama Index, or what have you to submit your prompts to LLMs. Specifically, I'm going to focus on temperature, top P, top K, and logit-bias. Maybe you've heard of these things before. Maybe you've seen them in the documentation. Maybe you've even used them but didn't quite understand what was going on. I'm going to hope to demystify them for you in this video. Another title for this talk might have been Struggling to Remember Your College Statistics Class, because in fact, I struggled to remember my college statistics class when working through some of this, because it does involve some statistics. It's not very complicated. It's fairly easy statistics to follow along with. I hope you aren't too overcome by it. Probably not going to be a problem. You're probably going to be able to figure it out with no issue whatsoever. Just know that this is statistics oriented. And I will be using some charts to help you visualize how these various options apply and how they influence the results that you get back from an LLM. Let's just say that we started with the phrase, I have a large collection of, and we ask the LLM to pick the next token. Now, that's how LLMs work. That's how generative AI works, is it's simply doing a march through a set of probabilities, picking the next thing that it thinks should follow. It's not much different, really, in the big scheme of things from how the completion on your phone works when you start texting somebody and it's recommending the next 3 words and you pick which word you want. It's not much different than that. It's based on what you've already said so far. It's picking the next word. It literally, that's what it amounts to. And so the LLM is being asked to pick the next token. Now, as humans, tokens aren't a complex idea, but it's easier to talk about words than tokens. Tokens are, as a rule of thumb, about 3/4 of a word. And since it's hard for us to talk about things in that unit, in 3/4 of a word, for the sake of this discussion, let's pretend that LLMs actually are picking words at a time and not tokens at a time. Will make things a little easier to talk about. Just know that in reality, they are picking tokens, 3/4 of a word, or roughly, some fraction of a word at a time, and not entire words. Okay? It just makes it easier to think about. So that's what we're going to do. We're going to talk about words. Now let's just say after we said, I have a large collection of, the LLM determines that there are 5 potential candidates. Now, in the real world, it's probably going to have several more candidates than 5, but it's easier for our heads to hold 5, so let's go with 5 candidates. And the candidates that it has chosen are books, coins, records, arts, and stamps. Now, each one of these has not only been chosen, but the model has also assigned to them what's called a logit. Now, a logit is essentially just a relative score of how confident the LLM thinks that should be the next token chosen. And so the logits can have any value on them, but it's just a relative score. For example, here is how we might distribute the logits across books, coins, records, arts, and stamps. Books maybe has a 2.5 logit, coins has about, I don't know what that is, 1.8. Records have some smaller value to that, and so forth. Now, the thing about logits is while they're good at kind of giving an idea of what the relative scoring is, they are very useless as probabilities because probability has to add up to 1. These don't add up to 1. You can't use logits when you're working with probabilities. And so there's this formula called softmax. And what softmax does is it takes the logits of a group of items and normalizes them into probabilities. So when you apply the softmax formula to these logits, here's what you get. You have books have a slightly less than half a chance of being chosen, or half of probability of being chosen. Coins less than half of that. Records half of that, and so forth on down the line. Now we have a set of probabilities that all add up to 1, and that's good. Now we can do things with it. And the reason that's important is because when the LLM is choosing the next token in line, or in our case, next word in line, when it's choosing the next token in line, it literally picks randomly. It randomly picks what the next thing should be based on these candidates that it has been given. But the randomness is not purely random. It is weighted. So in this case, books is going to have a higher weighting than coins, and coins a slightly higher weighting than records, and so forth, and the weightings are based on their probabilities. So as a consequence, if you said, I have a large collection of, there is a chance that any of these could show up as the next term from the LLM, but books are going to be chosen more often than coins, and coins more often than records, and so forth, because their probabilities are higher, and therefore those probabilities have weighted the random selection. All right, so then, now that we know what the probabilities are, how does temperature apply? Well, temperature is it's a scaling factor on the probabilities. When temperature is 1, it's essentially dividing by 1. Therefore, when you divide anything by 1, you get the original value. Therefore, when you're calculating softmax with a temperature of 1, you're going to end up at the same values you'll get if you really weren't even considering temperature. But the temperature is applied in the form of dividing the logits by whatever the temperature is when doing the calculation. And so as a consequence of that, when the temperature is higher, let's just say temperature is 2, then what happens is the chart tends to kind of even out a little bit. It never evens out perfectly even, especially with the temperature of 2. And the temperature of 2 is typically the highest value that you can give to an AI to calculate these probabilities. But when the temperature is 2, it tends to even out more. You notice it's a much flatter chart than when temperature was 1. As a consequence of that, this is why the things you may read about temperature tell you that when the temperature is higher, you get a more random answer. And the reason is because as it's being randomly chosen from this set of items, based on a weighted randomness that's based on the probabilities are much closer to each other. Therefore, there's a more equal chance of any of these being chosen when the temperature is higher. On the other hand, you may have also read or seen before that when the temperature is lower, it's more deterministic and less random. And the reason for that is if you apply a lower temperature, let's just say 0.5, then what you get is things like books have a much higher probability than they did before. Coins has a slightly lower probability, and then it gets even smaller for records, arts, and stamps. Now, what you may have noticed is that as temperature approaches 2, the chart tends to flatten out, but as temperature approaches 0, then what's clearly happening is the winning item, in this case books, tends to get greater while all the other ones decrease. So when we go to when we go to temperature of 0, this is what you end up with. Now, because it is in the formula, we are dividing by temperature to come up with this probability. When temperature is 0, you would normally get a divide by 0 error. But that's a special case because as temperature approaches 0, the probabilities of everything but books was also approaching 0. Then we go ahead and just assume that when temperature is 0, then that's the case, that books is going to be the winner and everything else is going to be 0. Now, this is what is meant by when the temperature is low or 0, you're going to have a very deterministic answer. Okay, well, you're not going to get a perfectly deterministic answer, and part of the reason for that is the floating point mathematics that are involved in calculating the softmax may not be perfectly correct, and also more importantly, if there are any items that are sort of tied, they have a very close or equal logit in the beginning, then in the end their probabilities are going to also be equal, and we have to have a tiebreaker. We have to pick who's going to win, and different libraries have different approaches, different models have different approaches of sorting out that tiebreaker. But for the most part, temperature of 0 means you're going to get a very deterministic answer every single time, and a temperature of 2 means you're going to get a very random answer every single time. Okay? Well, that's how temperature works. Now, let's go back to temperature equal 1, or not even applying temperature, where the probabilities are all sort of distributed based on their logits. And let's see how top P applies. So in this case, we're back to our original probabilities, and now we're going to apply top P. Now, the way top P works is it starts at the top of the chart. I mean, at least conceptually starts at the top of the chart. It's not quite the same, but conceptually, it starts at the top of the chart and it starts calculating the sum of probabilities for each of those items. And the moment that the sum of probabilities exceeds the top p-value, in this case, I've decided that top p is going to be 0.8. As soon as it meets or exceeds top p, we're going to draw a line. Everything else gets excluded. So in this case, when top p is 8, then arts and stamps are going to completely be eliminated from consideration. We're left with books, coins, and records. With those selections now being the only selections, we're going to redistribute our probabilities, and now we end up with something like this. And now you can tell that's a fairly flat chart. We've not applied temperature, and so it's a fairly flat chart, and this is going to be fairly random as a consequence of that. Now, it is not recommended that top P and temperature be used together, and a lot of that I think has to do with the fact that how do you know which one gets applied first? Because it is kind of important. If temperature gets applied first, then you would end up with maybe one term that meets the top P before you get very far at all. Or if the top P is applied first, then temperature gets applied later and you end up with a slightly different distribution. Regardless, I don't know. They tend to say that you shouldn't use them together. They recommend you not use top P and temperature together. But I have heard of folks who are finding some value in doing that. You just know that it's not recommended, but if you know what you're doing, go for it. I'm not going to judge. All right, that's how top P works. Top K works similar to top P. Top K starts by at the top of the chart and working its way down, but instead of calculating the sum of the probabilities, it simply does a count. So in this case, if top K is 2, we're simply going to take the first 2 items and everything else gets eliminated. So in this case, we're going to be left with books and coins. Records, arts, and stamps are going to go away. After we've done that, after we've eliminated those 3, we're left with books and coins. We redistribute the probabilities and we're left with something like this. And then again, the LLM picks the next token randomly, but randomly based on the weight of each token. Finally, let's talk about logit-bias. Logit-bias takes us to the very beginning, where we had not yet calculated probabilities. We had not yet applied softmax. So we're going to start off with the base logits. Here we're looking at the original logits we had at the beginning of this video. What we're going to do is when you apply a logit, you apply a logit bias, that is. When you apply a logit bias, you apply it to one or more individual tokens, or in this case, words. So I'm going to pick on coins. We're only going to apply a logit bias to coins. And what it basically a logit bias does is either add or subtract some value from the logits, and then that becomes its new logit before it goes into softmax. Okay, so here we have coins with a logit of about, 1.7. And let's just say we added a logit bias of +1. That's going to make it about 2.7. Okay, now that's its new logit. That's going to be fed into softmax, and as a consequence, the probability of choosing coins is going to be greater than books, where before books had a higher logit, therefore it had a higher probability. Okay, let's see what the probabilities end up being for different values. So when logit bias is 0, we're back at our original probabilities. Roughly half for books, half of that for coins, half of that for records, and so forth. But when we add a +1 logit bias to coins, we end up with this. Now coins are not quite, but nearly twice as probable as books. And records, arts, and stamps, they're still on the chart, but barely so. They're barely hanging in there. Now let's just say we applied a logit bias of -1 to coins. If we did that, well, then we end up with this. Basically, coins went much lower than books and still even lower than records and arts. Still higher than stamps, though. But because we applied that logit bias, coins is less likely. Books more or less stole the probability that coins lost when it got an adjusted logit. Now, in an extreme case, you might want to do this. You might want to add a logit bias of +100. And let's just say we did that to coins. Here's what you get. you're basically guaranteeing that the next token chosen will be coins. Now, I will warn you against setting logit bias this high for any term. It essentially guarantees that that is going to be the next token. And from experience, I can tell you what happens. Your answer will be coins, 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 coins for forever. You're going to end up with an enormous, huge response that's nothing but the word coins. And the reason for that is you've just said, by saying logit bias is positive 100, you've just said coins must be the next term because all the other ones fell off the chart. So typically you don't set logit bias that high. That seems like a foolish thing to do. Most oftentimes, depending on the probabilities and the original logits, what you're going to probably do is apply a logit bias of maybe +1, +2, maybe even as high as +5. Once you get past +5, it usually the benefits of doing it sort of fall off, and you don't want to do that anymore. But on the other hand, let's just say you set a logit bias of -100. This is what you end up getting. You get books with a high probability, records, arts, and stamps with a much lower probability, but coins is gone. Essentially, by setting something with a logit bias of -100, you are saying, I do not want this in the answer. And so if you, let's just say you had a term that was perhaps offensive, or maybe it hinted at some other brand other than your company's brand, then maybe you want to keep that word out of the responses so that it won't be confused with maybe the other company's brand, or so you won't offend anybody. Then you would set logit bias to 100 to guarantee it won't show up in there. This is also a fun thing to try. I've set logit bias to -100 and then asked the LLM to give me a recipe for ice cubes, but I set the logit bias to -100 for the term water. And it was an interesting response. It fell all over itself trying to tell me how to make ice cubes without using the word water. I was expecting it to give me something like H2O or something, but no, it struggled to come up with a good answer for me without using the word water. So, it's kind of fun. You should try it. It's a fun little experiment to play. But again, most of the time, you're not going to be set logit biases this low unless you explicitly want to remove a term from consideration. You're typically going to set it somewhere between a range of -5 and +5. And, your results will vary depending on what your needs are. But give it a shot, test it out, see how it goes. Thank you very much. Thank you for tuning in. Thank you for watching. I hope you learned a little something about how these various knobs can be adjusted when you're submitting prompts to an LLM. I hope you understand that a little bit better than you did before. And it doesn't matter if you're using Spring AI, if you're using LangChain, if you're using Llama Index, if you're using Semantic Kernel, whatever it is you're using, it doesn't matter. At the end of the day, all of these things are ways you can adjust the outcome of your prompts. Now, I would say one last thought before I move on from that. Top K is not supported by all APIs. In fact, OpenAI itself does not support adjusting Top K on your responses. At least it currently doesn't at the time I'm recording this. But Ollama does. If you're working with models in Ollama does support specifying Top K. All right. With that said, check out my books. They make great gifts. Spring AI in Action is currently available in early access at manning.com. There's currently 4 chapters in there as I'm recording this video. More will be coming, of course. And it will cover before we're done all the aspects of building great generative AI applications in Spring with Spring AI. Also, check out Spring in Action. Spring in Action, the 6th edition. It's going to cover everything you need to know about getting started with Spring, Spring Boot, Spring Security, things like that. And then finally, build talking apps for Alexa. It is easily one of the funnest things I've ever done is build voice applications, and I enjoy doing that so much so that I wrote a book about it. So check that out. But regardless of whether you buy my books or not, I thank you again for watching. I hope you learned something, and happy coding.